What is the grandest oversight in the universe? In 1985, scientists believed they had found the answer. A team from the Harvard-Smithsonian Center for Astrophysics, led by John Huchra, completed a survey of thousands upon thousands of galaxies in the direction of the Coma cluster. But as they organized their data, they noticed something strange: a colossal shape, spanning hundreds of millions of light years, slowly coming into view. The shape looked like a person, a stick figure, with a long, thin body and outstretched arms and legs poised to leap. But this was no mythical monster. It was our first glimpse of a supercluster, and more importantly, it wasn't the only one. It was later discovered that there are about 10 million such superclusters in our observable universe. Each one contains thousands, even hundreds of thousands, of galaxies. Our own Milky Way is part of one, nestled on the edge of the Laniakea supercluster. These structures are truly immense. The smallest span hundreds of millions of light years, woven from tangled threads of galaxies, while the largest can stretch for 10 billion light years, possessing the mass of over a quadrillion suns. The superclusters nearest to us are named for the constellations we gaze through to find them, such as Coma Virgo, Hydra Centaurus, and Pavo Indus. More distant ones are usually just known by a catalog number, unless they break a record like the King Ghidorah supercluster. It's one of the most massive ever found, discovered by Japanese scientists in 2002 and named after Godzilla's three-headed foe. And even though these superclusters hold countless galaxies and stretch across unimaginable distances, seeming impossibly vast, they are, in reality, quite small. Because in the universe, there is something on a scale that dwarfs them completely: the void. The truly largest structures are, in fact, made of nothing at all. Before we truly begin our exploration, take a moment to whisper a small wish into the quiet of the night. You never know, it just might come true. The story that follows is rich with detail, so listen closely and drift peacefully to sleep. As vast as these superclusters are, they're not the grandest structures in the cosmos. The truly largest thing is emptiness itself. It is not a mythical beast or a monster from the movies, but the very opposite, a hollow space in the darkness. Most of the universe is actually empty. In the voids, there is no starlight, no ribbons of gas. They cannot even be observed directly. We can only find them by seeing, where there is nothing at all. These cosmic voids are the largest structures in the universe. They dictate where the superclusters form and, in doing so, have shaped our very existence. Everything we know, our solar system, the Milky Way, our entire supercluster, is all suspended on the edge of a void. And in the end, the fate of the universe itself will be decided by these empty spaces. Our story takes us back to 1978 with astronomers Laird Thompson and Stephen Gregory. They had begun an arduous task at the Kitt Peak National Observatory, southeast of Tucson, Arizona. For nearly a week, they stayed up through the nights, precisely recording the positions of dozens of galaxies. Once their locations were confirmed, they fed the light from the telescope into an early electronic amplification device, a technology that was a precursor to our modern digital cameras. This allowed them to see incredibly faint and distant galaxies, peering deeper and more broadly into space than had ever been possible before. They were gazing into depths of the cosmos no human had ever seen. After amplifying the light, they directed it into a spectrograph. From the spectrum, they could measure a galaxy's redshift, which in turn allowed them to calculate its distance from us. In those days, there were no computers, no complex algorithms. All of this work had to be done by hand. Their goal was to create a map of a patch of the sky, not just plotting the positions of galaxies, but also measuring their distances. And while other astronomers had conducted similar surveys before, Thompson and Gregory employed two techniques that had never been used in cosmology. The first was the light amplification technology. The second was neither a technology nor a theory, and it didn't even require any profound understanding. It was a simple chart, a new way to visualize the distribution of galaxies. The diagram looked like a slice of pizza, with Earth at the very tip and the galaxies fanning out from near to far. This simple visual was revolutionary. It allowed them, for the very first time, to see the grand scale of cosmic structure in a single, clear picture. They had originally set out to study the famous Coma cluster, hoping to distinguish which galaxies were true members of the group and which were simply scattered in the foreground or background. But they found something else entirely. A vast, empty region, completely devoid of galaxies. This place, where countless galaxies should have been, was utterly barren. It was like a flaw in the fabric of the cosmos. And it was this new mapping method that made the emptiness so starkly apparent. On their chart, the dense collection of dots was the Coma cluster, surrounded by a few scattered galaxies, but in between, there was nothing. And so, they gave this empty space a name: the void. When Thomson and Gregory published their findings, the astronomical community was not convinced. Many were deeply skeptical. Some even voiced outright opposition. The thinking was that the universe had already been well mapped. Galaxies were supposed to be spread throughout the sky. They suspected the two astronomers must have made some kind of error. Perhaps there was a flaw in their observational design, or maybe their eyes were simply tricked by the image, seeing an emptiness that didn't truly exist. Perhaps deeper observations would reveal it was all a misunderstanding, a finding fueled by a desire to make a splash. At the time, the prevailing belief was that the universe couldn't possibly have such vast, empty regions. Nature, after all, abhors a vacuum. The void they had found simply shouldn't exist. But then, just a few months after Thomson and Gregory published their findings, astronomers and theoretical physicists from Estonia and the Soviet Union conducted their own independent observations in a different part of the sky. They too came to a similar conclusion. While their study didn't use the pizza slice chart, it also recorded large voids in the distribution of galaxies. And, more importantly, in contrast to the prevailing view in the West, Soviet scientists had already been actively looking for these very structures. Back then, the dominant theory in Western cosmology was the principle of large-scale homogeneity. It proposed that on a large enough scale, all regions of the universe are statistically the same. Of course, the distribution of galaxies might differ slightly here and there, but on the whole, it was thought to be uniform. While astronomers had long been aware of galaxy clusters, they were seen merely as local fluctuations with slightly higher density, not as grand structures in their own right. For scientists in the West, voids simply didn't fit into their models, but Soviet scientists saw things differently. The Soviet theorist, Yakov Zeldovich, proposed an alternative model for how cosmic structures evolve. He suggested that vast sheets of matter would collapse and fragment, gradually forming smaller and smaller clumps, like clusters and galaxies. In this model, voids were a natural outcome, the inevitable empty spaces left behind as the universe evolved. It wasn't until 1981, when American astronomer Robert Kirshner made another observation in a completely different direction, that the Western scientific world finally began to accept that voids were real. He and his team discovered what is still considered one of the largest voids ever found, the Boötes void. This void was larger than any single galaxy, larger than any cluster of galaxies. Within their observational field, the Boötes void was the largest structure of all, a vast, empty expanse that dominated their view of the sky. The original void found by Thomson and Gregory was officially named the Coma void. The existence of these two immense voids forced astronomers to finally acknowledge their existence. But this, in turn, raised even deeper questions. How did these voids come to be? And more importantly, how could a universe that was supposed to be smooth and uniform allow for such massive inconsistencies to exist? The discovery of these great voids marked a turning point in cosmology. The universe was no longer seen as a sea of randomly scattered galaxies that occasionally clumped together. Instead, the cosmos revealed a far more delicate structure. The clusters of galaxies were still there, but they weren't isolated islands. They were like bright knots, connected by long, slender filaments of galaxies. These filaments wove themselves together, creating vast structures, like great walls stretching between the voids. But even grander than these structures were the spaces between them, the voids that were first met with such doubt and later accepted. These empty expanses pushed cosmologists to completely rethink the structure of the universe. By the 1980 seconds and 90 seconds, scientists were beginning to understand that the universe could still, perhaps, be called uniform, but only if one zoomed out to a truly enormous scale. Galaxy clusters were not the final frontier of cosmic scale. Even the smallest of the cosmic voids were far more voluminous than the clusters themselves. More importantly, these voids didn't exist in isolation. Together with the clusters, the filaments, and the walls, they all formed a single, grander entity. To map this immense structure, one that included both voids and clusters, became the new challenge for scientists. And, in observation after observation, they discovered more voids, and larger ones, some even more vast than the Boötes void, or the Coma void. With each new discovery, scientists kept asking the same question: have we found the limit? Is there a scale at which the universe finally becomes uniform? And as they pursued these questions, astronomers realized they were stepping into uncharted territory. They were beginning to see that the universe was not the smooth, orderly place we had once imagined. It was more like a vast, cosmic web, intricate in its structure, constantly evolving, and boundless. We don't know who made the Laniakea globe, but we can confirm it was created around the year 1510. This was less than 20 years after Columbus reached the New World. On this globe, the outlines of Europe, Africa, and Asia are roughly accurate, but their proportions are clearly distorted. Only the southern part of South America is drawn. North America is just a series of large islands, while Australia and Antarctica are completely absent. Off the east coast of Asia, in a region known mostly through sailors' tales, a Latin phrase is written, "Hic sunt dracones," here be dragons. Although this phrase appeared on only a very few maps, the sentiment it expressed was quite common on medieval charts. It was an age just beginning, an era of global exploration, trade, and conquest. With every voyage, people learned a little more about the world, but they also discovered more unknown blank spaces. Faced with regions on their maps they couldn't depict, cartographers faced a problem. What should they draw in these empty spaces? Their answer was to fill them with mythical creatures like dragons, sea serpents, and lions, partly to spark curiosity about the unknown, and partly as a warning that beyond the known world lay unseen dangers. And this fear of the unknown did not disappear with the end of geographical exploration. The nearest large astronomical structure to our local group is a galaxy cluster. It's called the Virgo cluster, named for the constellation we see it in. A galaxy cluster is the largest gravitationally bound structure in the universe, like a dense city of galaxies, sometimes containing thousands of them. Spanning millions of light years in diameter, the Virgo cluster is about 65 million light-years away from us. At this scale, we are truly beginning to see from a cosmic perspective. The Virgo cluster is itself the heart of an even larger structure, a supercluster. Superclusters are the most densely packed regions of matter in the universe. These structures are not yet fully gravitationally bound, meaning the galaxies within them are still in the process of forming, not yet completely pulled together. They are still evolving. The supercluster we belong to is called the Virgo supercluster. The name is a bit redundant because the Virgo cluster lies right at the core of this supercluster. This supercluster contains not only our local group, but also dozens of similar galaxy groups. However, recent studies have revealed that this so-called Virgo supercluster is just one branch of an even larger structure. This more immense structure has been named Laniakea. In Hawaiian, this means immeasurable heaven, a fitting name. Laniakea has 4 major branches, including the Virgo branch. Each branch is so massive, it could be considered a supercluster in its own right. The entire structure is composed of about 500 galaxy groups and clusters, and over 100,000 galaxies, forming a vast, branching, interconnected megasystem that stretches over 500 million light-years from end to end. Comparing Laniakea to a single galaxy is like comparing a city to a single person, and considering that each galaxy contains tens or even hundreds of billions of stars, Laniakea is like a metropolis housing trillions upon trillions of lives. The number of stars within it is comparable to the total number of ants on Earth. Beyond it lie the Hercules supercluster, the Shapley supercluster, the Pisces Cetus supercluster, and many more. Farther out, there are so many known superclusters that we can't even name them all individually. They are simply designated by numbers, cataloging their positions and member galaxies. All of these interconnected superclusters together form the largest structure in the universe, the cosmic web. The cosmic web is the largest structure in the entire observable universe. This web is formed by superclusters linked one to another, stretching and intertwining like vines across the entire 9.5 billion light-year observable range. Within this cosmic web, superclusters are connected by long, slender filaments of galaxies, and between these filaments lie enormous galactic walls that partition the universe into different regions. The scale of the cosmic web is difficult to describe. If you were to compare the Milky Way to the cosmic web, it would be like a single cell to a human body. But even this analogy isn't quite right. To be truly accurate, you would need to shrink that cell down by another 1,000,000 times. The cosmic web is so immense that a single galaxy is like a mere point of light, and within each point of light, there are actually hundreds of billions of stars, spanning 100,000 light years. And yet, despite how breathtaking these superclusters are, the volume they occupy in the universe is almost negligible. In terms of volume, the universe is almost entirely empty. Apart from the galaxies buried deep in the cores of clusters, most galaxies actually live on the edge of the void, never far from its deep abyss. This is why the name cosmic web is so fitting. Just like the threads of a spider's web, which are visible but take up very little space, the glowing galaxies of the universe illuminate its filaments and clusters, but they are almost insignificant compared to the void. It's not easy for scientists to map the void nearest to us because these regions are both enormous and empty. It takes large-scale, comprehensive observations just to trace their outlines. At present, we know that. The closest void to the Milky Way is called the local void. Its diameter is nearly 200 million light-years. Farther away are the northern local supervoid, the southern local supervoid, the giant void, the Boötes void, the Coma void, and others. As our observations peer deeper into the cosmos, we continue to discover more of these empty regions. They are scattered irregularly between or around superclusters, and although they are called voids, they are not actually completely empty of matter, a fact that surprised early astronomers. But these regions are indeed profoundly lacking in galaxies. However, countless tiny particles, hydrogen and helium atoms, cosmic rays, neutrinos, and the afterglow of the cosmic microwave background radiation are constantly traveling through the voids. But the density in these areas is extremely low. By cosmological standards, if a region's average density falls below 20% of the cosmic average, it can be defined as a void. And the average density of the universe is already incredibly thin, about 1 hydrogen atom per cubic meter. In comparison, the density of a typical galaxy is millions of times higher. This means that deep in a void, aside from the occasional hydrogen atom or a passing cosmic ray, you could be millions of light years from any galaxy or celestial body. This is the loneliest place in the universe. These cosmic voids are not just empty spaces between galaxies. They are also nearly devoid of dark matter. We know that dark matter makes up most of the mass in the universe. For nearly every galaxy and every galaxy cluster, over 80% of its mass is dark matter. It's a completely invisible substance, made of a particle not yet identified by modern physics. This dark matter doesn't just exist within galaxies. It also forms the very backbone of the cosmic web. The galaxies we see are really just small beacons of light in a cosmic web of darkness, metaphorically revealing the underlying structure of dark matter. So, the entire cosmic web is actually made of dark matter, and the voids are places where there is almost no dark matter. We can't directly observe the distribution of dark matter because it doesn't emit light, but we can reconstruct a complete picture of the cosmic web through computer simulations. In these simulations, the densest regions of dark matter correspond to galaxy clusters. Filament-like strands of dark matter connect the galactic filaments, and in the emptiest voids, the distribution of dark matter is also at its lowest, which is why there are no galaxies. Projects like the Sloan Digital Sky Survey have already discovered tens of thousands of voids in the universe, but even so, these discoveries still only account for a tiny fraction of the entire cosmos. The smallest voids have diameters of 20 million light-years and are usually embedded within larger galactic structures like small pockets of emptiness inside superclusters. But the largest voids span immense cosmic scales, separating different superclusters by distances of 1 billion light-years or even more, and it is within these enormous voids that we begin to encounter a perplexing problem. Although early cosmological simulations can explain the formation of voids and superclusters, observations show that some voids seem to be too large, so large, that they defy our understanding of the laws of cosmic evolution. They perhaps shouldn't exist. Some voids are not just large, they are unbelievably large. They are called supervoids. Imagine an enormous cave hidden just beneath the Earth's surface. In Vietnam, a logger searching for timber accidentally discovered a cave entrance. He heard the sound of flowing water from within. Curiosity drew him inside. It was pitch black, but the movement of the air made him feel as though he had entered a massive space. A strong wind seemed to blow from the depths of the earth, but after returning home, he couldn't remember the cave's location. It wasn't found again until 20 years later, in 2008. That year, he led the British Cave Research Association back into the cave. Several expeditions finally revealed its full extent. This place, named Sun Doong, which means Mountain River Cave, is the largest natural cave in the world, with its own ecosystem and climate. It had been hidden underground for millions of years, almost completely unknown. And the universe, too, hides something similar: giant caverns hidden between the clusters of galaxies. We call them cosmic supervoids. They are more immense than any galaxy cluster, filling the spaces within the cosmic structure. We are only just beginning to comprehend their depths, but these supervoids weren't always so vast. Just like galaxy clusters, filaments, and walls, the voids too have an origin. They originate from minuscule quantum fluctuations in the cosmos, tiny variations in density within the quantum foam. 13.8 billion years ago, these tiny disturbances were magnified during the era of cosmic inflation. This hypothetical event, which occurred less than a second after the universe's birth, expanded the entire cosmos by an unimaginable factor. It also stretched these minuscule quantum fluctuations into density differences on a macroscopic scale. From then on, evolution was driven by gravity. Regions with slightly higher density exerted a stronger pull, attracting even more matter. This runaway effect intensified, eventually forming the cosmic web, a structure of galaxies, clusters, and the filaments connecting them. Meanwhile, the regions with slightly lower density, the voids, grew ever emptier during this process. Like underground streams slowly carving caves out of rock, the cosmic voids were steadily hollowed out. This matter was pulled toward surrounding galaxies and structures, allowing the voids to expand and grow. Unlike galaxies, voids don't collide and merge. They simply expand slowly. When a wall of Bratgov galaxies separates two voids, those galaxies are eventually pulled away, drawn toward regions of higher density. The wall thins, and the two voids eventually merge into an even larger one. There are no violent collisions, no explosions, only an ever-expanding emptiness. This ambiguity in their boundaries also made it difficult for scientists to clearly define a void, until cosmologists in recent years borrowed a method from geography known as watershed analysis. In geography, researchers often use watersheds to analyze the flow of water. This approach helps us understand things like ecosystems, the spread of pollutants, and the distribution of groundwater. A watershed is an area where all water flows toward a single outlet, usually demarcated by ridges or highlands. For instance, with rainfall on the continental United States, Part of it flows to the Pacific Ocean and the rest to the Atlantic, with the Rocky Mountains acting as the Great Divide between these two systems. Scientists have applied this same concept to the structure of the cosmos. If we imagine the high-density regions of the universe as mountain ranges and the voids as valleys, then we can analyze the flow of matter just as we study terrain. Imagine pouring water across the cosmos. It would naturally flow from the high-density areas down into the deepest parts of the voids. This cosmic watershed technique offers a clear definition. A void is simply a region of the universe with the lowest density. Their boundaries are delineated by the surrounding structures. Using this method, astronomers combine data from surveys like the Sloan Digital Sky Survey and the Dark Energy Survey to map tens of thousands of voids in the nearby universe. And what's more fascinating is that the interiors of these voids are not just random empty spaces. While most bright galaxies reside outside of them, scientists have discovered that some faint, reddish galaxies do exist inside, and the distribution of these galaxies within the voids is not random either. Further analysis reveals they form a kind of miniature cosmic web of their own, with small clumps of galaxies and delicate, filament-like structures. And between these tiny filaments lie even smaller voids. It's like a vast cave system with a main chamber connected to countless smaller caverns, separated only by thin walls. Simulations suggest that cosmic voids may have a multi-layered, nested structure, voids within voids, and within those voids, even smaller voids. This hierarchical structure even has fractal-like properties, with similar patterns repeating at different scales, each level nested within the last. Although we cannot directly observe all of these hierarchical structures because most of the dark matter is invisible and only a few galaxies dot the space with light, through simulations, we can still glimpse the outlines of this intricate structure. So, a question lingers. Does this nested pattern ever end? Are giant voids like the Boötes void the largest that exist? Or are they merely parts of something even vaster, a piece of an even larger supervoid? A clue to this may come from a very unexpected place: the cosmic microwave background. The largest voids in the universe might not be just a conjecture from simulations. Some clues come from our observations of the universe's very first light. The cosmic microwave background, or CMB, is a faint glow of light from about 380,000 years after the universe began. Back then, the universe had a temperature of about 10,000 Kelvin and was incredibly dense, like a searing ball of plasma. As the universe expanded, it gradually cooled, and the plasma transformed into neutral gas. The universe became transparent, allowing light to travel freely. Those very photons are still journeying through the cosmos to this day, and they are what we now observe as the CMB. The CMB isn't perfectly uniform. Its temperature fluctuates by about 1 part in a million. Some regions are ever so slightly colder, and others slightly warmer. Scientists use these minuscule differences to learn about the structure and composition of the early universe. But there is one exception, an anomaly known as the cold spot. It is both vast and frigid, far beyond what current theories can explain. It's an anomaly that the standard model of cosmology simply cannot account for. Some have speculated that it could be the mark of our universe brushing against another. But a more likely explanation is that the cold spot is caused by a colossal supervoid, influencing the microwave background we observe. This supervoid wasn't there from the start. Like other cosmic structures, it formed gradually as the universe expanded. When photons from the microwave background traveled through this region, they entered a void that wasn't yet very deep. But because the void was so immense, it took these photons hundreds of millions or even billions of years to pass through. During this time, the void continued to expand, its gravitational well growing shallower. So when the photons finally emerged, they had to climb out of a gravitational well that was, in effect, deeper than the one they had entered. This journey resulted in a loss of energy, creating the cold spot we observe today. This supervoid, linked to the cold spot, is known as the Eridanus supervoid. But it's not the only one. Other supervoids have been found, such as the Canes-Venatici supervoid, also called the giant void. It lies 1.5 billion light-years away and has a diameter of 1.3 billion light-years. And the largest of all was proposed in 2013 by 3 astronomers, Ryan Keenan, Amy Barger, and Laniakea. They named it the KBC supervoid, though some also call it the Great Void. This void may be the largest known, with a diameter that might reach an astonishing 3 billion light-years. What's even more mind-boggling is that even though our Milky Way is surrounded by massive structures like the Laniakea and Shapley superclusters, the volume of this supervoid is still vast enough to encompass them all, while still having a density below the cosmic average, fitting the definition of a void. They propose the existence of this void in an attempt to solve a long-standing problem, the Hubble constant discrepancy. There are 2 primary methods for measuring the rate of the universe's expansion. One method uses the CMB from the early universe, while the other relies on observing supernovae in the modern universe. The results from these 2 methods don't match. If we happen to be living inside a supervoid, where cosmic expansion is slightly faster, then our local measurements would naturally differ from those based on the early universe, potentially resolving the discrepancy. However, the existence of the KBC supervoid remains controversial. To date, scientists have yet to find sufficient independent observational evidence to confirm it. Regardless, the other supervoids we do know about are already unsettling our understanding of the cosmos. It's like finding a cave on Earth so vast that it defies all geological theories we would naturally begin to question our understanding of geology. In the same way, the universe's largest voids aren't just big. The scale of some of them is so large that it challenges our understanding of the fundamental principles of the cosmos. In cosmology, there is a key principle known as homogeneity. It means that on a large enough scale, different regions of the universe should be, statistically speaking, roughly the same. Scientists generally agree that this scale of homogeneity is around 300 million light-years, a view supported by solid theoretical grounding. From our observations of the cosmic microwave background, we know the size of the initial density fluctuations in the early universe. By combining that with the effects of gravity and the universe's composition, we can calculate how cosmic structures should evolve over billions of years. The results show that if we look at the universe on a scale of 300 million light-years, no matter where you look, the average density and the distribution of structures should be more or less the same. It's like taking a census. If your sample area is too small, say 100 kilometers across, you'll see vast differences in population depending on the landscape. Some areas will be bustling cities, others empty deserts. But if you make your sample areas large enough, each one will contain a mix of cities, rural areas, and open spaces. Overall, they will start to look the same. The problem is, the size of these supervoids exceeds this scale of homogeneity. In other words, these largest empty regions in the cosmos are bigger than the scale at which the universe is supposed to become uniform. This raises a core question. Are these supervoids just a few rare, random occurrences with little impact on the grand scheme of things? Or is our understanding of the evolution of cosmic structure fundamentally flawed? If a cave were discovered on Earth far deeper than theoretical limits allow, we would have to re-examine geology. Similarly, if voids exist in the universe that are larger than our calculations can account for, it might also mean that we need to revise our current cosmological models. The scientific community has no consensus on this. Some cosmologists believe that these supervoids are indeed too large, violating the fundamental assumption of homogeneity and suggesting we might be missing some new physics. For instance, an unknown fifth fundamental force, or a hidden form of energy in the universe. Yet, other scientists believe that even in our region of the universe, the occasional appearance of a supervoid is still within the realm of statistical probability. Some complex cosmic simulations also show that while the probability is extremely low, similar structures can indeed emerge. Although the debate is far from over, one thing is certain: these voids are still growing larger. The universe harbors many dangers. Some forces, by their very nature, are driven to grow, to expand and devour. Living organisms like viruses or bacteria have their growth checked by resource limitations. But on the grandest cosmic scales, no force can stop the endless expansion of certain things. Cosmic voids are not just empty holes in space. They were smaller in the past and are constantly growing. And according to the principles of physics, they cannot be contained. We live in an ever-expanding universe. With each passing day, the universe becomes larger than it was the day before. In a way, the average distance between galaxies is also increasing. While local mergers happen on a much larger scale, the universe as a whole is accelerating its expansion. This acceleration was discovered in the late 1990 seconds, when astronomers observed that the expansion of the universe was not slowing down but was, in fact, speeding up. To this day, we still cannot explain the cause of this phenomenon. Scientists call it dark energy. In the simplest models, dark energy is considered a property of space itself. Even if you were to remove all the particles and radiation from a box, that box would still be filled with dark energy. This dark energy exerts a faint, repulsive gravity. In regions of high matter density, like galaxies and galaxy clusters, its effect is negligible. But when we look at the universe as a whole, the influence of dark energy becomes dominant. This means that the only places in the universe truly dominated by dark energy are the voids. Those vast expanses with almost no matter are not truly empty. Though they lack stars and galaxies, they are filled with dark energy. Dark energy is like a force infecting the cosmos. It doesn't just sit quietly, it actively expands the universe. The voids aren't passively waiting for galaxies at their edges to drift away. They are on the offensive, pushing their boundaries outward, driving matter away, and leaving behind a cold silence. They are compressing the surrounding galactic walls, making them thinner, squeezing the filaments until they break. This process will not stop. On the contrary, as the universe expands further, the voids will grow larger, and dark energy will become ever more dominant. Scientists believe that dark energy began to dominate the universe's evolution about 5 billion years ago. From that moment on, the formation of cosmic structures began to wind down, from the initial chaotic state after the Big Bang, to the formation of galactic filaments, and then to the creation of superclusters. This grand evolutionary process is gradually coming to an end. Those vast structures, the superclusters spanning hundreds of millions of light years, will never truly be able to merge. The voids surrounding them over billions of future years will cut them off, isolating and tearing apart this cosmic web, pushing all matter further and further away. Eventually, the cosmic web will be destroyed, swallowed by the ever-growing voids. No more filaments, no more superclusters, no more walls. All that will be left are isolated galaxy clusters floating in an increasingly empty universe, forever unable to reach one another. This is the distant fate of the cosmos. The voids will ultimately triumph. They will leave no trace, taking with them the entire order and structure of the universe. The universe will eventually return to nothingness. But perhaps the greatest irony is that it is these very voids that offer us the best window into the universe's past. When cosmologists try to understand cosmic evolution, they generally have two options. One is to directly observe evidence from the early universe, like the cosmic microwave background radiation. But that is just a snapshot in time, a singular event, and the information it carries is finite. The other method is to study the structure of the present-day universe, the galaxies, clusters, and filaments, the walls and the voids, and, using the laws of physics, to wind back the clock and reconstruct the cosmic past. The various components of the universe, ordinary matter, dark matter, and dark energy, determine the way the cosmic web forms. For example, if dark energy were stronger, no structures could have formed at all. If there were too little dark matter, then galaxies could not have clumped together. This means the entire evolutionary history of the universe is written into this cosmic web. It is a vast treasure trove of data, recording how the universe evolved from an initial sea of plasma into what we see today, and it will also determine its future fate. In principle, we could even analyze the structure of a single galaxy or galaxy cluster to deduce its history. But in practice, this is nearly impossible. It's like the countless hydrogen atoms in your body. They have existed in the universe for over 13 billion years. Theoretically, we could trace the history of these atoms, reconstructing every event they participated in, but doing so is practically impossible. The same is true for galaxies and galaxy clusters. They are too complex, containing processes like star formation, magnetic fields, supernovae, and cosmic rays. These complex processes have obscured their early traces, making them difficult to decipher. But voids are different. Voids are simple, empty, and stable. They change very little. Over billions of years of cosmic history, they have remained almost undisturbed. They simply grow larger slowly, occasionally merging with a neighbor. Compared to the dramatic evolution of galaxy clusters, voids are practically cosmic relics. They are like time capsules, the most pristine preservation of the early universe. If you want to know what the universe was like billions of years ago, the best way is to look into the depths of the voids. And more importantly, voids are filled with dark energy. Although we know that dark energy may exist in every cubic centimeter of space-time, in dense regions like galaxies and galaxy clusters, complex physical processes make it difficult to study its fundamental nature. Only in the voids, these vast, clean, and nearly interference-free regions, do we have a real opportunity to study dark energy and understand its impact on the fate of the universe. For decades, cosmic voids were overlooked. They were once thought to be just blank spaces on maps, observational errors, or random gaps in the distribution of galaxies. The scientists who first discovered these voids were even ridiculed because, at the time, no one wanted to believe that such vast regions of absolute nothingness could exist in the universe. But in the last decade, this attitude has begun to change. With the development of new technologies, scientists can finally use tools such as the watershed algorithm to systematically search for voids within vast amounts of galaxy survey data. Today, astronomers have compiled catalogs of tens of thousands of voids, a number large enough to make voids a central focus of cosmic research. In 2023, the European Space Agency launched the Euclid Space Telescope, embarking on a massive galaxy survey mission to map the positions of millions of galaxies. This mission has a dedicated void research group, aiming to use these empty regions to better understand dark matter and dark energy. NASA's future flagship mission, the Nancy Grace Roman Space Telescope, has made similar preparations. It also has a dedicated void research team. More and more researchers are realizing that voids are not just blank spaces, but gateways to deeper truths. If we want to understand the deepest mysteries of the universe and test the limits of our existing theories, or even move beyond them, we must learn to face the abyss. We once wrote, "Here be dragons" on the edges of maps because we feared the unknown. And now, as we gaze into the depths of the cosmos, the true unknown is no longer a monster of our imagination. It is these quiet, cold, expanding voids. They do not roar, they do not burn. Yet, in the most silent way imaginable, they are rewriting the fate of the entire universe.